So I'm going to introduce our speaker. We have Darren Smith here today, who is a master's graduate of Carleton University, Canada, and a senior geologist and project manager with Dahrouge Geological Consulting Limited. With offices based in Alberta and Colorado, Dahrouge Geological provides professional geological consulting and project management services, as well as a variety of expertise to the mining and mineral resource industries over a large array of commodities. Darren's primary role with Dahrouge is a high-level project management, excuse me, to the mineral exploration industry, including program design, data capture, reporting, land management, corporate disclosure, as well as Indigenous peoples and government engagement. While he has provided technical oversight for several preliminary economic assessments, as well as pre-feasibility and feasibility level project advancement, his primary focus and interest is carbonatite complexes and associated metals, including niobium, tantalum, scandium, and rare earth elements, as well as fluorspar. His talk today is focusing on the dominant commercial rare earth elements and their characteristics, which are the key to economic production and a long-term, secure, and strategic supply. All right, Darren, the floor is yours.
Thank you very much. Good afternoon, good evening, good morning, depending on where you are. Thanks for the opportunity. So as Wren was noting, I'm a geologist in the industry. I'm project manager for Commerce Resources Corp Bathurst Rare Earth Deposit. And I've been working in rare earths since about 2008. And before that, I had a few years in the uranium industry. But my main interest and work has been rare earths. So I'm a geologist, is what I do. I'm not an analyst. I work on exploration, and my goal is to make discoveries for clients and basically build shareholder value and find a deposit, and that can be exceedingly difficult. The chances are about 1 in 1,500 from an exploration project to a discovery. So I'm going to talk today about rare earth elements, specifically market mineralogy, and these considerations that help push this to push the economics of such deposits. Okay. Cautionary statements. Okay, the basics. So the rare earths are essentially the lanthanide series, and what makes them very unique is they always occur together. So when you have a rare earth mineralization, you just don't get one rare earth, you get them all together. They always occur together in the same minerals. And this is a function of their unique chemistry. They're both trivalent states, similar ionic radii. And so they all behave very similarly and occur within in the same minerals. I'm just going to state them out and then chat a bit more about them. So the actinides are lanthanum, cerium, praseodymium, neodymium, promethium. Promethium it doesn't really exist very well in nature. It has due to its decay, there's only about 600 grams that exist at any time in the Earth's crust, and so it really only exists in nuclear fusion or in the sun, for example. So when we talk about rare earths, we don't actually include promethium. Samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, ytterbium, and lutetium. And my son's learning to read now, and we're going over the periodic table, and it's quite funny when he gets to the lanthanides. Yttrium we also include as a heavy because they tend to occur together. They occur with the rare earth. So when you have a rare earth mineral, you're going to have some yttrium in there. Scandium, depending on the source you go with, if you're in the academic industry or engineering or chemist or how have you, scandium may or may not be included. In terms of mineral exploration, we never include scandium, and the reason is it simply doesn't occur in the same minerals. It might occur in an amphibole, for example, which can collect a lot of things, but amphibole is not a rare earth mineral. So when you're processing a rare earth deposit, there might be scandium in there at a decent head grade, but it goes everywhere in the flow sheet for the most part. So recovering scandium is not typically really done in the space. The rare earths were first discovered in 1787. It took over 100 years to discern them all. The first use was cerium and thorium lamps, and then later flint is mish metal. The rare earths never occur as a metal themselves. They have to be processed through. But they really didn't take off into use until there was efficient separation techniques that were developed, and that was in the 50s and the 60s. And so basically that is when you start to see rare earth uses picking up and all those unique properties being put to use in society. There are light, middle, and heavy rare earths. Again, it depends on your source, but essentially your lights are lanthanum to neodymium, your middles are SEG, samarium to gadolinium, and your heaviums are terbium over. Europium is not considered a heavy. You'll sometimes see that in industry, but it's more of a promotional angle because the europium price at one point was $5,000 a kilogram. Right now it's about $29 a kilogram. And so it helped a lot, certain aspects of the project by referring to europium as a heavy, but it is not a heavy, it is the middle, or you could call it a light more than you could a heavy. Also, I've read a bunch of articles on rare earths. I see them come out every other day in the news, and there's some confusion sometimes. I've seen rhenium described as a rare earth. That's not it. Graphite was one I read the other day. That's not a rare earth. Indium, gallium, these are not rare earths. So when we talk about rare earth elements, they're really this set of 15 elements, which include yttrium. Crustal abundance versus global production. So rare earths are common in Earth's crust. They're much more common than, they're more common than commodities like copper or lead. Cerium is more abundant in copper, for example. Neodymium, praseodymium, yttrium are more common than lead. So, but they're recovered in much smaller amounts, and it's because they're rare earths are relatively common in the Earth's crust, but they're very difficult to concentrate in economic concentrations, and that's really the crux of everything. There's a lot of rare earth deposits out there, but only a small fraction of those have any chance of actually being economic, and there's a lot of factors that go into that. And the rare earths were initially called rare because they were very difficult to separate at first. It took over 100 years to separate them all and get all 15, and so that essentially is where that term comes up with. They're relatively easy to separate now with solvent extraction. You can get to 5-9 purities down to 1 ppm impurity, but they're initially very difficult to separate, hence the name. Global production is about 202,000 tons a year. It was about 130 about 5-6 years ago, so it's gone up in a significant clip, and that includes all the rares. So this is the sum of all 15 recovered. And of course, compare that to copper and lead, it's relatively small. Sometimes these elements are referred to as specialty metals or technology metals. And sometimes that loose term is sometimes defined as something that's less than 150,000 or 200,000 tons a year production. Yeah, rares cumulatively are about 200,000, give or take. And rare earths in resources and reserves is always expressed as oxide. It's never expressed as metal, so it's not like copper, you express that as a metal and so on. For rares, you don't. You express it as an oxide, and that's the base how it's priced and traded in. Okay, rare earths permeate our lives in a lot of ways, and they permeate the hybrid electric vehicle and the electrical vehicle industry. Your car has hundreds of micro motors in it. You know, my car is 5 years old. I think there's 5 little actuators just on the seat to adjust everything. And, you know, cars now have little actuators to turn your lights when you turn. All these little things use magnets. And really the crux of rare earths is magnets, and we'll get into that a little bit more. And the miniaturization that these rare earths allow for magnets, they allow you to make very small motors. But rare earths are also used in a lot of other things, yttrium for sensors and phosphors. You have glass polishing with cerium. A large use of cerium is glass polishing. Nickel metal hydride batteries, about 10% of those batteries are rare earths. So if you think of all your AA and AAAs lying around that are nickel metal hydride, those have rare earths in them. Tesla used to use induction motors, but they changed those to permanent magnet motors after the Model S and early Model S and Model X series. And the new Model 3 around 2017, they came out with permanent magnet motors. And at the end of the day, they're far more efficient. And when you have an electric vehicle, you want to have light. You want to have small magnets. You want to lightweight it, and you want to have the most efficient motor that you can. And this is what rare earths give you. Yeah, and also catalytic converters. So if you're not an EV, you have a catalytic converter, and this helps clean the exhaust, and a lot of rare earths are used in that as well. Okay, so that's your EVs, which is obviously a driving force, but REs permeate your everyday life. So wind turbines, for example, there used to be, you know, less than 3 megawatts. Now they're significantly larger, and they're going offshore. These use significant amount of magnets, neodymium, iron, boron magnets, and neodymium, dysprosium, terbium, and praseodymium are the main components in those magnets. You can use over a ton per turbine, depending on its size. So these magnets are critical for this, and they allow you to do a direct drive in your wind turbine. So this gives you less maintenance, less moving parts. And when you're offshore, this is very, very important. To repair a turbine well offshore is quite expensive. So you want to have something that has the lowest percentage of failures possible, the least amount of maintenance. Siemens has gotten very, very good at this. NdPr is used in welding visors, for example, to protect your eyes and so on. Lanthanum is used as your fisheye photo lens. Cerium is used in water filtration. Fuel cracking catalyst is a huge consumer in the North American market. So cerium and lanthanum are used in that. It's about 3.5% in the catalyst is cerium and lanthanum. Praseodymium, I read once that it was used to make the beautiful yellow color in Lego. I doubt it is anymore, but it was pretty interesting. Erbium and fiber optics and 5G. So you think about 5G coming around, there's a good demand for erbium and that for your fiber optics. And lutetium is the least abundant rare earth, if you will. And the running joke for a while on lutetium was the main use of lutetium was to study lutetium, but it has a lot of uses in applications such as lasers and in industries associated with that. And of course, phosphors, yttrium, europium, terbium used to be used in phosphors as well, and so on. And power tools. So basically, you can imagine if you're a construction worker, price isn't going to be your main pinch point. It's going to be ergonomics, lightweight, that sort of thing. So transitioning from ferrite magnets to rare earth magnets is pretty important for handling your tools. And of course, new emerging markets. So I saw a presentation by Ryan Cassidy of Adamas Intelligence, and I'll have a lot of his charts in here. He's a very, very excellent analyst in the rare space. I highly recommend him. And he gave a talk a few years ago and pointed out the robots in the industry. So you think of the number of multi-purpose industrial robots, per 10,000 persons employed in manufacturing industry. You can see China at 49, South Korea way up there. And we know that China is pushing downstream. They want to transition from low-tech assembly and integration to high-tech design and automated production. And with this, you need more robots. So their robot density needs to increase by an order of magnitude. Each robot has around 16 kilograms of neodymium-ion boron magnets in it. So this is quite significant. So that's one major growth area. Other growth areas are refrigeration, magnetocalorics, I think it's called. Is another one. And these are small penetrations, but have explosive growth potential. And also for neodymium-ion boron magnets, just recently, to think of consumer electronics, all the smart speakers you get, all these other things around, you have explosive growth into making that technology smart. And to do that, you need magnets and you need rare earths. Your phone vibrates. I'm sure most people have their phone on mute right now or on vibrate. That is a little rare earth motor that's spinning around, and they're a haptic feedback engine that is making it vibrate, and that is done by a rare earth magnet. There's only less than maybe a few grams of rare earths in your phone, maybe 5 cents to a quarter of value, but they're absolutely essential for these things to work. Okay, volume and value by end use. So, you can break uses of rare earths in various categories: batteries, catalysts, ceramics, glass polishing, metallurgy and alloys, permanent magnets, phosphors, and so on. Phosphors essentially being lights, if you will. And you can see catalysts is large volume, and this is because of cerium and lanthanum. A lot of that is produced, the easiest to produce. But you can see permanent magnets makes up almost a third of the volume of rare earths right now. And that comes down to essentially 4 rare earths: praseodymium, neodymium, terbium, and dysprosium. But if you look at the value, it suddenly shoots up to 91%. So when you look at this, when you look at a rare earth deposit, you get all 15 rare earths at once. You have to process them all together, but only 4 of them are going to drive the value of your deposit, just 4. And the industry reports REO, deposits are done in total REO, but it really is those 4 that drives the value. And you see this every time you look at a Linus presentation. They're focused on NdPr because that is where their value driver is. And so projects will make or break on the percentage of magnet feed materials they have. So the growth is down this year simply because of COVID, but it's going to recover strongly. And Adamas Intelligence expects almost 10% compound annual growth rate from 2020 to 2030 for these magnet feeds. and supply is going to have a lot of trouble keeping up with demand, and there's going to be new sources that are required. All right, just a couple comments on magnets. In the rare space, we talk about magnets a lot, but we don't really say much more about it. So I just want to put a slide into for some pointers for people. So this is neodymium iron boron to samarium cobalt. Samarium cobalt was first developed in the 1970s. It's a good magnet, but when we talk about magnet feeds, it's not really, doesn't really carry a lot of value. So really it's all about neodymium ion boron, and samarium cobalt really focus on a certain niche market. So the main thing about neodymium ion boron is it's a maximum energy product. It is the strongest magnet. If you can think of buckyballs, 5 years ago, you get a set of buckyballs, all little magnets go together and they're hard to pull apart. Those actually got banned for a while because kids or dogs would eat them and it would screw up their intestines. There are incredibly strong magnets. If you have two of them together, it's incredibly difficult to get apart. There are some drawbacks to them. They're limited to operating temperatures. Your typical neodymium iron boron magnet might operate up to 80 degrees Celsius before it starts to degrade, but you can dope that with terbium and dysprosium, the heavies. This is where those two come in, and they allow you to boost that operating temperature up to 140 plus, depending on the type of magnet. There's many types of magnets. They do tend to corrode, so they must be coated for protection. So when you're looking at a neodymium iron boron magnet, you're actually looking at the coating, nickel plated or something like that, because they tend to corrode. Samarium cobalt, roughly a third to half as strong as neodymium ion boron. It maintains performance at high temperatures though, and this is critical for niche applications, for defense industries, for things like this. Samarium becomes pretty critical for that. It's very good against protecting from corrosion. So this is important if you can think of marine applications using magnets and pumps or whatever that have to go in a marine environment. You want to have something very resistant to corrosion. They're also more expensive to produce. So at the end of the day, cost is a major factor. So if we look at neodymium ion boron magnets versus ferrite, ferrite's also known as ceramic. They're about 1/10 to 1/20th the strength of your neodymium ion boron. Strong resistance to demagnetization is a big positive. They maintain performance at high temperatures, very good as well, and they have good resistance to corrosion, but moreover, they're cheap. And so this is where you have the trade-off. My car, I think, still has ferrite magnets to move the actuators to move the seat, but those are being replaced in EVs and so on with rare earths, because you want a low weight, you want to make motors smaller. And as you get into your electronics, you want to use neodymium ion boron. You think of big wind turbine, weight is a big issue. You'd have to have a much larger ferrite magnet to do the same thing you could do with a neodymium ion boron. So it's very important. And cow magnets, for example, I actually grew up on a farm, and you had to put cow magnets into the cow, because when they eat grass and everything that's there, and they pick up nails. And so the cow magnets are actually ferrite magnets that go in their stomach and collect that stuff. So there's a use for ferrite magnets where there is not a use for neodymium ion boron. There's a balance problem that happens. In rare earths always occur together. So you just don't find a deposit of just neodymium. It doesn't happen. That has all your other rare earths in that mineral. So they always occur together. Therefore, they're recovered collectively to an intermediate product. So you mine your deposit, you beneficiate it, you get a mineral concentrate, hopefully of pure bastite or monazite that has loaded with rare earths, and then you have to crack it and get all your rare earths out. Now, all those rare earths have such similar chemical affinities that they all come out together into an intermediate product, which is basically a mixed rare earth carbonate, could be an oxalate product or a rare earth chloride product, but that is your sort of base saleable product to most separation facilities. And now you still don't have your neodymium, you just don't have all your gangue. Now you just have your pile of powdered rare earths. So you have to separate that. And this is where solvent extraction came in. And in the 50s, this became really important. They were able to start separating rare earths. And the color televisions was a big thing with Mountain Pass. They would separate europium out, and that europium was used to make the red color and color televisions. And so once you get to this intermediate oxide, you have to separate it. And this is just solvent extraction. It's a method to separate compounds based on their relative solubilities into different immiscible liquids. And so basically, we're fortunate in that promethium doesn't really exist, so it allows a nice separation coefficient. between your lights and your middles. And so you can break out your lights first, and then you can go down through your separation. And if you focus on where the green and the red is, those are your heavies and your lights. So your green is your praseodymium, neodymium, your lights. And then your heavies are your terbium and dysprosium. So again, those are the four that really matter. Everything else has very low value, but you have to process all the way through to get to those. So you're going to produce a lanthanum product and a cerium product. And if you go all the way to terbium and dysprosium, you're going to produce a lot of other products, and that's going to offset the market. If you want to process everything, it's more than 1,000 stages. It's a significant amount of processing. Typically, you have facilities that separate only light rare earths. You have ones that separate only heavy rare earths. You might have one that do cerium, lanthanum depleted and separate just the magnet feeds. So these you can't just change tolerances in these facility. They can only handle so much tolerance in terms of different amounts of rare earths in the mix. And so that's why you have some that are focused just for lights and so on. Because we're lucky, we can do at least that one separation. So another part of the balancing problem is there's differing markets. So you may target NdPr, but you're going to produce a lot of cerium and lanthanum, and that doesn't have a lot of the same markets. You can make low grade magnets with cerium and dope them with cerium and so on, but it doesn't have the market as NdPr, which drives the economics of everything. So this is going to lead to an overproduction of your cerium and lanthanum. The offsets of this are it could lead to an increase in price of NdPr to offset the cost of producing these lower value rare earths, but it's also going to provide incentive for or for R&D into new uses for these lower value REEs. And we've already seen that when you give smart people money and they'll do wonderful things. And PVC stabilizers is something, for example, the cerium lanthanum can replace the old chemicals used in that and help with PVC stabilizers. There's also cerium alloyed engine blocks for high performance. So you can think of this being adopted by race cars, for example, would be the first thing used for that. So lots of R&D. De-icer, for example, when you're sitting on your plane, how many of us have sat there in the winter just waiting for the de-icer to happen, spraying over? But what if you could put a cerium compound on there that would not allow ice to form? These are some things that have been developed, or products won't stick to your plane and stuff. Or ketchup packets, much ketchup do we waste in our ketchup packets when you squeeze it all out? But if you have some of these new technologies that are being developed with cerium involved, it'll allow all that ketchup to just slide straight out of the package, for example. So there's a lot of engineering and work going into that. And there's a lot more going into the lights, because magnets use a lot more neodymium and praseodymium compared to heavies. So for example, your neodymium ion boron magnet will have about 30% neodymium, and part of that will be praseodymium. They occur naturally at about a 3-to-1, 4-to-1 sort of ratio, with neodymium being the more. And so sometimes you'll get them both in there. Your praseodymium helps with corrosion resistance, and your neodymium is your main performer. But if you want that to work at high temperature, you have to put a little dysprosium and terbium in there, maybe 1% or 2 sort of thing. But those are also the more expensive rare earths, as we'll chat about a little later. So, okay, this is probably the most complicated slide in the talk. And I guess focus on the highlighted areas. These are your magnet feeds. So this is if you got a pile of rare earths, that mixed intermediate product, 1 kilogram of it, and it was sitting there in a pile, no other gang or other stuff in there, just rare earths. This is how much each of these deposits would contain. And so in rare earths, we have a price for every single rare earth, but really at the end of the day, it's only your practical price deck needs to assign a 0 value to your cerium, your lanthanum, your yttrium, and so on, because at the end of the day, they're not going to drive the value. These projects need to be able to produce profitably using just these price decks. So basically, your mag feed percent at the bottom is really the most important. So the mag feed percent is the percent of your total REO grade that carries the value of the deposit. So 100 minus mag feed is percent of the lower value oxide present, if you will. So the higher your mag feed number, the better. And that's the most important thing here, because when you look at it on a 1-to-1 basis, for example, Mountain Pass will have, if you have 1 kilogram rare earth oxide sitting in a pile, they'll have 16.4% of that is the good stuff. The rest of it will be the low value. If you have Mount Weld or Ashram, for example, you have around 24-25% of that material, the good stuff. So on a per kilo basis, they actually have more valuable material than Mountain Pass. But these prices don't take into account tonnage and grade, for example. It's important to realize that Mountain Pass can overcome its poor distribution because it has a much higher grade. So it produces a lot of material, and that can overcome it. When you look at, say, a clays tend to have very low grade, but they have very good distributions. What they produce is the best stuff, has the highest value. So they can overcome their lower grades because there's a significant amount of tonnage and they're very easy to process. And so basically in the rare earth space, you get your magnet feeds in terms of neodymium and praseodymium. They dominantly come from your light rare earth deposits, which are carbonatites. We'll chat about that in a few minutes. And you dominantly get your heavies from your clay deposits. And so in current foreseeable market, your magnet feeds are what are going to drive it. And this is really what you need to look at for all rare earth deposits. What is the percent of their magnet feeds, and can they process that out low cost? If it's complicated mineralogy, complicated metallurgy, it doesn't matter how good it is, sort of thing. So. Okay, so in the rare space, you hear a lot about China. China dominates the rare earth value chain. You know, about 10 years ago, they're about 97% of production. Now they're about 70, thanks to Mountain Pass and thanks to Linus at Mount Weld. And they both have very good deposits, excellent grades. Mountain Pass is very, very good mineral processing and produce a very nice concentrate. And Linus has been able to develop as well and produce a very nice concentrate. So they've been able to join the market. But China dominates. So the rare earth value chain is complex. It starts at the mining, then you go to a mixed rare earth oxide product, then you go to separated oxides, then you have to separate those, and you have to reduce those down to metals. Then you take those metals, then you have to alloy that with other materials, iron and so on. And basically you take that powder and then you have to make magnets with it. You get those magnets and you have to coat those magnets so they don't corrode. And then you have to put those magnets in housing, put those magnets in an actuator, put those actuators in a car, and suddenly your seat moves up and down. So the value chain is very intense, and the margins at all these stages are not all the same. And they can change over time as well. In China, they're very integrated. They decided this back in the 90s to do that. And so they have the mining, and they've dominated all the way down the value chain of the industry. And the reason they do that is because they have the resources and they've developed the technology when no one else was. And so, you know, at the oxide stage, the value of the market is probably around 3.5 billion. And it goes up, you know, 10 times when you hit the magnets, and then motors 100 times and so on. And you're in the trillions when you get down to the end use. So when you talk about value, you really have to figure out where you're talking about in the value chain. And so what the world is trying to do is trying to have security of supply and develop projects, but also other aspects of that value chain. There is some magnet making in a few other countries outside. There is some metal alloying happening in less common metals in the UK, for example. But at the end of the day, China completely dominates all these industries and that intellectual property as well. And you can see Mountain Pass back in the 80s, they dominated. It started with mineral sands, and then it moved to Mountain Pass when it was discovered. And basically it produced a lot of europium was the main target at the time for your red color in your televisions. But then Binoble came on, and basically it's the largest mine in the world. It supplies roughly around 40%, give or take, maybe a bit less now. And so they began to dominate, and Mountain Pass couldn't compete anymore. And then China used their mining and their upstream to basically, they subsidize their upstream through the value chain downstream. So they might lose money on the mining, for example, but they make it up further downstream. So basically China dominated the industry, still dominates the industry. And then in 2010, there was a boat incident with the Japanese, and suddenly they cut off supplies and to Japan. And this is where everything went haywire. Prices went crazy. Everyone was staking rare earth projects. There's over 600 projects staked at one point. A lot of that was moose pasture. A lot of great discoveries were made though, and new deposits were found. But again, you run into the problem of difficulty in the economics of making them work. So these prices went through the roof. Europium, for example, went up to $5,000 a kilo at the time. Neodymium went from under 10 or around 10 or so up to over $300. So they went quite excessive on the prices, and so this caused a lot of things to happen. Basically, caused a lot of people to look at the value chain, look at China, and realize what the dominance was, and then figure out okay, how do they address this issue of breaking up this. Not necessarily breaking up their supply chain, but augmenting it by other uses, or getting other development in there, so they can, like what the SRC has done, starting a separation operation, getting more metal reducing, getting the magnets, bringing it back out to the west, that sort of thing, and not having everything just done in China. So China is diversified. I want to show the one on the left because it's fairly representative. When you're looking at REO production and looking at it, it's really best to look at it from the mining, where the mine production comes from. So United States is Mountain Pass, Australia is Mount Weld, Burma is South China clays, and these are where most of your dysprosium and terbium come from. And then China, which is basically dominated by 2 mines. And then your India, Madagascar, and Thailand, these are heavy mineral sand. These have sort of been a consistent producer over time, but there's a very minor producer at this point. And then there's Russia, and Russia has a little loperite mine, which is very unusual mine, and rare earths are actually secondary to niobium and so on. But you can see China's very diversified in their exports of their magnets. Again, that's where the most value is, and you can see they're very diversified that way. And so what the world needs to do is be able to not just have China as their primary supplier. So what do high prices do? Well, they force a lot of money to be invested with a lot of smart people to come up with other substitutions. And a great example of this is phosphor use. So in phosphors, you have europium, which gives you this nice red color. Well, they figured out that you could just use an inert particle and coat it with europium and basically get the same effect. But not only that, you move from fluorescent to LEDs. LEDs last a lot longer, and they use fewer amounts of rare earths in them. And I believe they eliminated terbium from a lot of them as well. So you can see that. I mean, half the lights in my house now are LEDs, and they use very little amounts of rare earths, and they became accepted a lot quicker. And I imagine part of that is because of the high cost of europium. So a lot of the rare earth recycling that started was actually with fluorescence and trying to collect those phosphors out. You would see the most expensive part of a magnet, even though it's about 30% neodymium, the most expensive part is the dysprosium and the terbium. And the dysprosium and the terbium, the main function there is to help with demagnetization, but with operating at higher temperatures. And so there was a lot of work put on removing that dysprosium and terbium. It wasn't necessarily put on replacing neodymium. It was focused on removing that dysprosium and the terbium. And so a lot of these substitutions were actually with other rare earths. So cerium ended up being doped in to offset some rare earths, and actually helped with this neodymium. A bit more neodymium was used when you remove the dysprosium, for example. But not only that, they looked at really smart ways to reduce the amount of dysprosium and terbium and still maintain that performance at high temperature. So part of this was with grain boundary diffusion. So instead of your dysprosium mixed throughout your entire magnet evenly, sort of thing, giving you that effect, they were able to diffuse it around the grains, and you'd be able to reduce your amount of dysprosium significantly and get the same effect. And so you're before the rare earths really prices started going up, magnets could have up to 13% dysprosium in them. Now that's been reduced down to 2-3%, down to 0, but it's still required for critical applications. And a lot of work was looked into. Do I need to have high temperature in my application? Oh, I'll remove dysprosium. Do I need that much performance? Oh, I'll just dope it with some cerium and remove a little neodymium, for example, and you can reduce your price. So there's a lot of things like that done. And Siemens, I saw a talk a few years ago, and they basically developed a dysprosium-free magnet that'll work well in their turbines. And the way they design it is the airflow sort of goes around the magnet and cools it and so on, and allows them to operate their turbines, fewer dysprosium. So what does this mean? It means that when your prices went up, you had a lot of downward, you had a lot of pressure to remove dysprosium and terbium from your mix. And that led to potentially more uses of other rare earths. But moreover, if you're just a heavy rare earth deposit that is focused only on those heavy rare earths, and most of your value is in dysprosium or in terbium, the market constantly wants to engineer you out. And that's an important fact. Where if you're an NdPr, your light rare earth deposits, such as carbonatite, the market actually wants to engineer other uses for the lights that you're going to overproduce. So it's much better to have a light rare earth deposit that has a decent heavy contribution that you can recover, as opposed to potentially being one that's purely focused on dysprosium and terbium, because you're more susceptible to those sort of market risks, if you will. And a lot of work was trying to substitute neodymium at times as well, but they wouldn't have any success. Okay, so recycling, obviously high prices kickstart recycling, and recycling is a good thing. 30% of your copper market is essentially from recycling. Apple, a lot of ESG is been developed in a lot of companies, as it should. And Apple has, for example, launched this robot in 2016 called Daisy, designed to disassemble iPhones. And basically what it does, it disassembles the 9 versions of iPhones. It recovers about 14 materials from these iPhones, aluminum, tin, cobalt, rare earths, and then it takes those components out, and then it sends those components for downstream recycling. So again, it's only part of the chain of recycling, but what it shows is that there's work going on to do this, to increase recycling. Recycling by end use, rare earths, is very low. It's less than 1%. And part of this is because the long use of some of the materials, but also because in your cell phone, for example, the main way that you're going to be able to recycle these components from your phone is for the design of the phone to change so they're easily extractable. If it takes a lot of work to extract that taptic engine, to open it up, to get your rare earths out of there, that's only 2 or 3 grams. I mean, it has to cost less than the 25 cents of that part, sort of thing, for example. So it's important to note that redesign is a very important aspect. This machine can do about 200 phones an hour. Sort of thing. I think they came out with a new one recently called Dave or something like that, and it does a bit more, but it will remove that taptic engine, but there's another series that has to be done in order to get the magnet and the rares out of that. Where recycling is really started to take off is sort of in magnets. So when you make a magnet, there might be 30% more material that's used to whittle down to get to that final magnet. So the cuttings of it, grindings, all kinds of things that have to go in with that. And so basically, this is called swarf and various other materials. And this is material that can be recycled. Sometimes it might have to be demagnetized and redone in order to recycle it. Other times it can just be put back into the mix. So there is, out of the total NdPr supply, there is a large component that's actually coming from reusing the cuttings, if you will, for that. So kind of think is when you're, cutting cookies out of a baking sheet, there's always parts left around, right? It's collecting all those parts, putting it back in your dough, making more cookies. It's like that. And so there's a few companies out there. Geomega is another one that's trying to make it work in the junior space. I haven't got them mentioned here, but there's Urban Mining, Rocklink. RE Recycle is really interesting. They're recycling hard drives. Old hard drives have rare earth magnets in them. The new solid state drives don't actually have any moving parts. They don't actually have any rare earth magnets in them, but those hard drives are still quite good for large data centers and things like this, where a solid state isn't necessarily that important. So recycling is there, but it's difficult. It's not easy, and it's going to take redesigns, and it's going to be focused on what certain rare earths for recycling, if you will. Some cerium is recycled in the polishing process and immediately reused, that sort of thing. But in total end use, it's very low. Okay, so where do rare earths come from? What's the production from? So carbonatites is the main production. This is 80% of rare earths come from carbonatites. Carbonatites are light rare earth enriched, which means they're going to have more neodymium, praseodymium compared to clay deposits, for example, or other deposits. And so they're going to have a lot more of that NdPr, which is good. And what I want to point out here is where the carbonatites are located, mostly in China. You can see the South China clays. There's some in Malaysia, North Vietnam. And those are where you get some of your heavies out of. So carbonatites are basically igneous intrusions. They're 50% carbonate minerals. You have a partial melt of the mantle. Rare earths are incompatible elements, so they partition to the melt. They ascend. They have a lot of CO2 in them, so they brecciate as they ascend and basically cause ring structures, brecciation, and you get your emplacement of your rare earths. They tend to come in the center of these larger complexes, and around the rims you might get niobium and things like this, but the centers tend to be more rare earth enriched. So you can see Mountain Pass there. You can see Linus over in Australia and in China. So, but what you also see is there's a lot of peralkaline igneous rocks. And there's that one up in Russia, which is a low-pyrite mine. That one's very unusual. There's no other low-pyrite exploration projects out there that I'm aware of. And it's also recovered as a byproduct of processing for niobium and so on. But peralkalines are very different. They're more granitic. They're going to have tend to be lower grade, and they tend to be more weighted in the heavies. And so their value is going to be more tied to dysprosium and terbium, for example. And of course, your heavy mineral sands, India, Brazil, there's some in the US, there's some in Australia. They're actually quite global, a lot of them. And this is where the historic recovery of rare earths has started with mineral sands, actually, monazite. That one at the very north of China, that's Bainobo. That's where most of your rare earth production comes from. And iron ore is actually its primary commodity. Rare earths are actually a byproduct. Okay, so rare earth mineralogy, it really all comes down to the rare earth minerals that you have. There's over 150, I think there's far more than that, but only 4 have been commercialized. So there's a lot of minerals that rare earths can sub into, but there's only a few that have actually ever been commercialized, and those are monazite, bastite, and xenotime. So one of the first things you should look for is, does the deposit have those minerals in it? They account for more than 80% of global production, current and historical. So it's important to note, look what producers have done in the past and in the future, and do they have that? On the right, you can see, again, just focus on the 2 highlighted areas, and those are your distributions of that mineral. So if I have a pile of just bastnasite, 13.5% of it is going to be neodymium, 4.4 is going to be praseodymium. Xenotime is the heavy rare earth one. It's mostly heavy rare earth sands. It can come in carbonatites or in vein systems, hydrothermal. And you can see that one has a lot more dysprosium and terbium in it compared to neodymium and praseodymium. So that's a sought after one if you're going after the heavies, for example. And why are these 3 minerals more important than all the rest? Well, that they allow you to make mineral concentrates of over 40-50% REO. And so you can concentrate your product up to that high, and so, or your concentrate up that much. So basically, if you have a full pile of it sitting there, it's gonna hold upwards of that 50 to 75% REO in it. And of course, the host rock type again is carbonatite. Okay, so these are RE contents of common minerals. So again, on the top, bastnasite, monazite, xenotime. These are the rare earth minerals proven to be commercially processable. So these are the ones that have been processed historically. There's known ways to mineral process them to concentrate them into mineral concentrates. There's known ways to put them into solution and to precipitate them out into a high purity product and to separate that. Parasite is similar to bastnasite. So it can be processed up as well. There's calcium in it that can cause some problems, gypsum formation and so on in the next stages. Gypsum can collect some air heavies and not put them into solutions, so it can be a problem. But if you look at the next part, some allanite, apatite, cainite, gadolinite, eudialyte. Eudialyte is often touted as a rare earth mineral because these eudialyte, for example, carries a lot of heavies in it. It doesn't carry a lot of light, so it's going to be very weighted to the heavies. The problem is if I have a pure pile of eudialyte, I only have an 8% REO concentrate. Nothing like that's been processed commercially in the past. And moreover, these minerals, these silicates and so on, they often, you have challenge processing. They're often associated with complicated mineralogy. So you might have cainite that can hold 38% rare earths in its structure, but the problem is that your deposit might have some cainite in there, but it doesn't have a lot, and it has another dozen other rare earth minerals in there. So now you're having to recover all these different rare earth minerals into one package in order to process it out. So your entire rare earth budget might not be just in cainite, for example. So the challenge with these is metallurgy, and it doesn't mean it'll never be solved. There's a lot of smart people that have looked at it. There's been a lot of money spent on processing eudialyte, and none of it's, you can process these, but it comes down to, can you process it economically and low enough cost? And so the issues with these are they put a lot of different elements into solution that complicate precipitation of your rare earths, and they often come with complicated interlocking mineralogies as well. Feldspars, these sorts of things. These are your peralkalins, granitics type deposits. And the ion absorption clays. So I've alluded to these a few times. They're very different. These are ions that are adsorbed onto the surfaces of clay minerals. There might be rare earth minerals there, but you don't recover them. You only recover these ions, these rare earths that are sticking to these clay minerals. And it's very low grade, less than 0.2%, but they are very easily recovered. With ammonium sulfate and so on, you could pee on them and you would liberate the rare earths off them. And so the problem with that is in China, there've been environmental issues and so on. So they're challenging economically process to Western environmental standards. And so that's important to note. But there are some companies that are looking at that, and they're mostly limited to South Asia, but there have been some that have been found elsewhere. So what do producers do? They make mineral concentrate. This is fundamental why these minerals are important, because you need to reduce the size of your hydromet and so on. You need to concentrate in order to move stuff downstream. So they take their whole rock, they beneficiate it with flotation, is the main method. Use gravity separation, various separations, but they make a rare earth mineral concentrate. Then they send these to their hydromet, and that is where they pour acid on it, they caustic crack it or sulfuric acid, and they break it down and put all the rare earths into solution, and they precipitate out a mixed rare earth product. So this is all your rare earths in a product sitting there in a pile. That now goes to solvent extraction for separation. You can imagine if you went the other route, the whole rock digestion, you basically are dissolving your entire deposit in acid. And then your hydromet plant is going to be significantly larger because you're going to have a lot more elements to deal with, a lot more complications to deal with. And this is going to cause your costs to go way up. So if you look at all the producers, all the hard rock producers out there, they all produce at least a 30% rare earth mineral concentrate, all the major ones. There's the one very small producer that produces 20% at the moment of xenotime, but all the major ones produce at least a 30% up, and most of them produce well over 40–50%. And it's because it's by far the most efficient route. And they process this to a rare earth carbonate, or it could be an oxalate precipitate, or an oxide, or a chloride. And basically these are feeds that go into your solvent extraction. The most common is rare earth carbonate. Most facilities can accept rare earth carbonate, and that's typically your intermediate product. So the benefits are fairly clear when you look at it like that. Lower reagent consumption, less acid required to break down minerals and place the REs into solution. So this is quite critical. If you need more acid, that's a lot more transportation. That's just a lot more cost, a lot more larger tanks and so on. There's a lot more CapEx and OpEx. Fewer deleterious elements. And if you talk to a metallurgist, the cleaner your solution is, the easier it is. And so you want to have a very good pure solution that's high concentration in rare earths. And to get the highest concentration or proper concentration, you want to have a very pure mineral concentrate. Lower hydromet throughput. the largest cost of most rare earth projects isn't the mineral processing or mining, it is the hydromet. And the hydromet is also the most technically challenging. So you want to minimize that as much possible. So it's absolutely critical that you mineral concentrate so you can have reduce the size of your hydromet plant and get it down smaller. And this is going to save you a lot of money. So this is going to also reduce your risk, your technical and your downstream risk and your costs. It's never a question of if you can make a rare earth product, saleable product. That can often isn't the issue. The issue is it can be done economically. And when you're looking at companies that are talking about mineral processing and stuff, it all comes down to how cost effective it is. And, we've chatted about mineral sands briefly. I'll touch on that again. Those are some of the lowest grade rare earth deposits in the world, and they can produce, they can go from 0.2% REO up to 65% REO. And they can do this because of very low cost processing, and they're very economic, and they also have natural byproducts as well in them. So all these aspects are very, very important. You need to mineral concentrate, and in order to do that, you need to have the right mineralogy. If not, then you have to deal with all these other issues, and that can often make or break a project. So mineral concentrates, this is what the major producers do. Binobo, they produce 2 concentrates. They're a very unusual deposit. It's, but rare earths are a byproduct of iron ore mining. And so basically, it's the largest producer of rare earths on the planet. Maiping is the second largest deposit in China. They probably has one of the easiest metallurgical flow sheets, and it can produce a very high grade bastite concentrate. Wushan is a smaller deposit, less known about it, but it as well produces high grade mineral concentrates. Mount Weld took them a lot of time on their mineralogy, but they were able to produce a 40% plus mineral concentrate for downstream processing. And most of these use flotation as their primary methods to do this. So very low cost methods. Mountain Pass, of course, bastite, very good grain size, can liberate it well and basically can produce high grade. That Carnoustie one, that's the loperite one I had alluded to before. Again, unusual, but again, they produce 30% REO mineral concentrate. That's essentially a pure loperite concentrate. And of course, these placer deposits located globally, they do the same thing. So again, no major producers down there. 90 or 80+% is produced by this, and the remainder is your ionic clays. So you need to have the right mineralogy. You need to have a carbonatite. You need to be able to economically process it. Not all carbonatites are going to be the same. If you have a granitic granitoid deposit, it doesn't mean you won't be successful, but it means there's more hoops you have to jump through. There's going to be more R&D and capital investment to solve some of these issues and get around the issue of not being able to upgrade. And a big change in that regard over the last 10 years has been XRT sorting. This can be very effective for certain projects and removing gangue and feldspars and stuff. So that's something that has helped granitic deposits. But at the end of the day, this is where what past production is shown, this is where current production is shown, and this is where it's going to go in the future. Okay, heavy mineral sands. So heavy mineral sands is where it sort of started. Basically, they're the dominant supplier of rare earths through 1965. Monazite is the byproduct of primary rutile and ilmenite mining. So this isn't like they're just mining for monazite. They're actually, the economics are driven by rutile and ilmenite, but they can recover monazite as a byproduct. And so these things are formed, if you can imagine, a beach development environment, and then you have the constant waves crashing, or you have a storm come in that pulls out all the lighter sediments and basically concentrates the heavier sediments. And then that storm goes away, and then you have more beach buildup, and those sediments get buried and so on. And so you can have this happen over 100-kilometer strike lengths, 10 to 15 meter depth sort of thing. And if you go to the beach, you can sometimes see it happening in real time, how that works. And you can see these heavy minerals. So you get your ilmenites, your rutiles, your zircons, and your monazites are all around 4+ in specific gravity. So these tends to concentrate in your heavy minerals. So this is why we call it heavy mineral sands. They tend to be they can be very large tonnage, but they're very low head grades at 0.2. But the key to their economics is monazite, the right mineral, and low cost processing. It's dirt easy to process by comparison. Gravity, magnetics, electrostatic. They're not using a lot of reagents or these sorts of things. They're using a lot of physical methods to upgrade it. And they can take this 0.2% up to 60+%. And so that this helps it a lot. So that's the dry mining method there. They strip off the top, they remove the sand, and then they put back down the topsoil after to remediate it after and collect the sand. And these are still happening today in the US and so on. These are, it's a gravity flotation plant there. And the artificial lake is is dragged behind a dredge that continuously moves as it mines the sand, delivers it to the gravity plant. This gravity concentrate is pumped to a dry plant on the land. You can see the wet screening of the heavy mineral sands, the spirals on the right-hand side. So this is simply gravity. You pour it at the top and it comes out the bottom and it segregates, and basically you collect it and so on. And your dredge just collecting all the material, electrostatic to separate it. And at the end, you can come out with nice concentrates of each product that you're looking for. Some of these pictures are from Sierra Leone and the old Asarco mine in Manchester, New Jersey. It doesn't exist anymore, is where some of these photos are from. Okay, this is the product. This is the heavy mineral sand, 60% REO, and there's two main things to look at this. One is the rounded grains. They're fully liberated, so this does not require any blasting or this sort of stuff. It's already unconsolidated material. This really helps in mining it and allows for this efficient separation. It's also coarse grain size, which is pretty important as well. The finer grain you go, the more difficult things can get. If you get too fine, then these methods wouldn't work. But because of these sands are like this, you get very pure mineral concentrates. So this is such high grade, they can actually do a caustic crack process and recover the phosphate out of the mineral and have another byproduct out of it that way. So this is a very nice pure monazite concentrate product. Ion absorption clay deposits. So again, these are clay deposits. These happen from granites, weathered granites. Granites in tropical environments. Granites tend to be naturally enriched in heavy rare earths. And so as you weather these over long periods of time in certain environments, you're going to build up that process will turn your feldspars and so on to clays, and then your rare earths will be liberated and attach on and so on, and you get your rare earths absorbed to clays. There might still be rare earth minerals there on some clay deposits, but so your recoveries might appear to be low because you're recovering all the ions, but you're not recovering the actual, if there's any minerals there. And so this is the Benden deposit in Vietnam. These tend to be very low grade. So 0.05 to 2%. So we're talking, 500 ppm, 1,000 ppm, and so on. And they're the dominant source of heavies because they tend to have affinity for the heavies. But there's also wide variation. There's sort of a type A and a type B deposit. You can see on the right-hand side the distributions again, and you can see there's one that has a lot more neodymium than the other. And so that one that is I'm not even sure it's Jinwu. I'm not even sure. It's a very good distribution. When you're above 20% neodymium, you're doing pretty good. And so these are large tonnage, very low grade. So that doesn't sound too positive so far, but because it's low cost processing and they can be recovered easily, they are economic, and they're often sold to market as a blend of mixed REC. So you don't produce mineral concentrates with clays. So the mineralogy isn't applicable, all that mineralogy discussion. This is a completely different game where it is clays, and you skip the mineral concentrate stage because there are no minerals. You go right from these rare earths into solution, and you precipitate them out into a mixed product, and you sell that. In China, for example, you basically you sell your mixed rare earth carbonates. You also have bastnäsite, monazite concentrates that you sell, or monazite concentrates that you sell, and those are sort of the main aspects that are traded around there. And for this would go directly to a solvent extraction facility to remove. And because it's heavy weighted, it would go to a specific facility that it has the tolerance and the number of cells and stages in order to separate that. This couldn't go to a light rare separation facility. It wouldn't be able to fit that tolerance. there are legal environmental issues with this method depending on how it's done. China is actively clamping down on illegal mining, improving environmental standards, but there's a lot of artisanal, sort of small mom and pop operations that were going on. And this couldn't happen in the West, but this is sort of what we are up against when you're trying to develop these sorts of deposits elsewhere. There's a really nice one in Chile and a few other places that they're trying to develop. And so they have to develop them to, more Western environmental standards. So part of the way China used to do this, well, there's two ways. One was they would just strip mine the hill and remove all the material. And you can see that on the on there. That's a picture of, I think that's Longnan. So these are all the areas that they've basically been stripped. And you can find that on Google Earth quite easily. And those little ponds are where they'll put the material in there and they'll precipitate it out. So this one caused a landslide that happened, and so that is obviously not good. The other thing I want to point out here is the pipes. So the other method that isn't just stripping is where they actually put pipes into the ground, and basically they pump the solution into the ground, and it basically removes the ions, captures it in the fluid, and they catch it at the bottom of the hill. So that's why you see those impoundments there at the bottom of the hill to catch the solution. So basically you're pouring, this dilute solution through your hill. So there's different methods of doing this. Some are better than others, but it's something that needs to be, it's a cost disadvantage that the West has. And there aren't a lot of these deposits elsewhere. You need tropical environments, certain conditions, so they are relatively rare. 10 years ago, they're really only known in South China and Myanmar a bit, and so on. So this is one in Vietnam. So these are precipitation tanks at sort of the bottom of the hill. And basically it's recovering the solution and it allows it to precipitate. This one's located about 200 kilometers west of Hanoi. The grade is very low, but the RE can be easily leached out with ammonium sulfate. So again, this is something that the West can't necessarily work to these sorts of standards. And by that comment, I mean referring to, the picture on the right, they're shoveling filter cake off a belt filter. This is something that, we probably wouldn't do in the West. It'd be mechanized, if you will, right? So there's different methods, different approaches. And for example, weather is obviously a big thing as well. If you're going to process these things, you can't necessarily process them outdoors. Okay, carbonatite deposits. I commented on a bit on how they're formed before. So basically, you have the partial melting. Your rare earths are partitioned to the melt, and then they rise. There might be crystal fractionation or immiscibility happening, sort of thing. But basically, it has a lot of CO2 in it, causes it to fracture when you get to the surface, and basically, all your carbonate minerals and high field strength elements basically crystallize, if you will. This is the Saint Aurore complex. This is the Niobec, basically where Niobec produces from. They actually produce niobium. They have an excellent rare earth deposit there at the center of it. It sort of fits the general model. Basically, carbonatites are very deep. They tend to, if they're plug-like, they can go down forever. At Ashburn, we've drilled 600 meters and it still goes and the grade gets higher. If it's a dike, at the outskirts of them, they can form dikes and sills and so on. Mountain Pass is sort of a giant sill dike, if you will. And so basically these are the dominant source of rare earths and where they're found. And they're the dominant source because of easy processing, because they have the right minerals that form here. You tend to get bastnaesites and you tend to get monazites that form in these environments. So this is Bionobo. So I've already mentioned it's the largest rare earth mine globally. It's rare earths are a byproduct of iron ore mining. It produces super high grade monazite bastnaesite concentrates. The deposit itself, it's a large deposit, it's about 6% REO, but there's various areas in it where the grade can go down to 1%, but they're still able to process this high grade monazite bastnaesite concentrate. It's also one of the largest fluorspar deposits in the world. I think it is the largest fluorspar deposit in the world. It's a large niobium resource and a large scandium resource. I don't believe they're recovering fluorspar yet. I think they're just looking at recovering scandium now. But it is unique. When you have one deposit that accounts for, upwards of 40%, give or take, of the total market, it's quite intense. There's you can see how it's sort of grown over the years in terms of doesn't look like it's necessarily planned out how it's spreading, but it's the processing there is not necessarily all done in the most environmental manner, and so they've been cleaning up their act a bit in terms of how they're processing it and stuff like this. But these tailing ponds and stuff like this, we wouldn't be able to work this way in the Western world, and so we have to make sure that it's done properly and so on, and it can be done that way. But this is going to continue to be a very large source. Miaoping, so this is in western, in the Western Sichuan province, and it's the Mine-Dashang REE belt. So it contains a lot of smaller deposits. The carbonatites tend to occur in clusters, and not necessarily, it's odd that they would occur just one-off, but they do tend to occur in clusters, and Miaoping is one of the largest ones. So it's very large tonnage, about 2 to 3% REO. Very high grade bastnäsite concentrate they get from this one. And it's very easy processing. They can get very high recoveries, upwards of 80+% recoveries into their bastnäsite concentrate. So it's an excellent deposit, and it forms a stockwork, if you will. So again, has the right mineralogy, has simple processing. They get high recovery because of it, and they can produce these high grade concentrates. So shipping these downstream to process through is going to have a smaller hydromet plant, lower reagent usage, and so on and so on. Mountain Pass. A lot of people are familiar with Mountain Pass. I just want to kind of, if you compare this Google Earth with the one at Bionobo, you can kind of see the difference in organization, if you will. They dominated the market from the 60s to the 80s, and they produce a very high grade bastnäsite concentrate. There's some monazite in there, but it's dominantly driven by bastnäsite, and they can produce a very high grade concentrate. And they're currently producing concentrate, and they're shipping it into China right now, actually, to process. There's not a lot of processing capacity, outside of China, for example. There's obviously Linus. There's Solvay that could do separation. I think they've closed down a bit or not operating right now. And there's a few other places, but for the most part, China does a lot of all that dominates that part of the market. And so they're also owned about 9.9% by Shanghai Resources, which is a fully integrated miner and processor in China. They're non-voting shares though. So as a decent proven and probable reserve, so it doesn't include resources, just proven and probable reserve. These grades change over the years depending on what your reserve is, so on and so on. And so right now it's around 7-8%. So very, very nice deposit. Very, it's right off the highway. Coarse grain bastnäsite is the main mineral. So the brown in that is the dolomite. The pink is your bastnäsite. Has a lot of barite in the rock as well. And so it's a very nice deposit. That is on the picture on the right, upper right, is from the birthday vein. So this is one of the initial discoveries of the deposit. It's more coarser grain than the actual deposit, but it's just off to the it's just off the deposit where that sample came from. Mount Weld. So Mount Weld is sort of the newest entrance. I guess Mountain Pass had produced for a while, then it stopped, then it started for 2 years, then it stopped, and now it started again. And Mountain Pass is touting they want to move downstream and so on, and that's great. That's part of the solution to the supply chain issue. For Mount Weld, so this is one of the highest grade rare earth deposits in the world. The probable reserve, proven and probable, is 8.5%. I mean, I've seen those numbers as high as 14, 15% at this deposit. It can be very high grade in areas, and it's a laterite. So your laterite's formed by intense weathering of your carbonatite, and basically your carbonates are broken down, your calcium and so on is removed. You get a lot of iron minerals in there, goethite and hematite. You get your rares kind of remobilized, and you get super G mineralization. You get super G monazite, crandallite, florensite, these sort of things. But you get a very fine grain size when you do it. So Linus is a fantastic deposit, has the right minerals, but laterite is the subcategory of carbonatites that adds more difficulty. because your processing is going to be harder. Part of this super demineralization is that it causes your grain size to get finer. And so their grain size can go to down to 5 microns or even lower at times. This makes it very difficult to mineral process. So they've put in a lot of effort, R&D over the years. Took them quite a while, a lot of investment, and they managed to solve a lot of these issues, and they managed to process this material, and they managed to process it up to about a 40% REO, which is pretty good. So remember, if you had a pure monazite concentrate, it would be around 65%, give or take. They're getting up to 40. So this is quite good that they've reduced a lot of the waste that'll go into the hydromet plant. And they've proven they can be successful, and they've leveraged mining at scale, same as Mountain Pass, produce over 20,000 tons REO equivalent a year. And so they've been successful in that. The mining concentrator located in Australia, the hydromet plant is in Malaysia. They're looking at building another plant in Australia for cracking due to environmental concerns around uranium and thorium, mostly thorium, I guess. Radioactivity is something that it's more of a it's not so much an environmental issue. There's a lot of regulation in place. There's a lot of ways to deal with these sorts of things. It's more of a social issue, and articulating that properly, and then make sure you're following the proper regulation. And so anyways, it's a very excellent deposit. They produce NdPr oxide, cerium carbonate oxide, lanthanum cerium product, and a mixed SEG. So this mixed SEG, that's samarium, europium, gadolinium, those are your mids. It actually includes heavies in there, but because Linus's solvent extraction facility they have, it only has so much tolerance. It's focused on the lights because their main value is NdPr. So they process that NdPr. So out of all those, the NdPr carries by far the dominant value of the project. And their facility is designed for that. So their facility can't actually process that SEG oxide. So they ship that into China to currently separate, but they don't get a lot of value for it. So they're going to build with Texas, a very good group in the US, very smart people, are going to build a joint facility to basically process heavy rare. So if that gets built, that's another piece of the supply chain that's put in place. And basically heavy rare separation is something that potentially be used by third parties in a toll process or someone who knows exactly, but I'm sure this is something that's been thought around. But it's an excellent deposit. It's a world-class niobium deposit, a world-class tantalum deposit. It's another one of those one-offs that is like buying oboe. It's an exceptional deposit, and they've done a great job in advancing it and still going on. A lot of the material goes to Japan. Japan has supported them ever since the China-Japan row happened in 2010. And this is another big reason they've been able to get off the ground. So Japan has actually started to diversify their supply because a lot of it comes from Linus. So a lot of smart people working at Mountain Pass and Linus. This is I'm not sure how to pronounce that, Yanfu deposit. Another deeply weathered carbonatite. This one's quite unusual. It's a low tonnage producer, 1 to 2% REO, but it's got xenotime. So this is going to be your heavies, your dysprosium and your terbium, what you need to make those magnets work at high temperatures. Again, everyone's trying to engineer you out, but xenotime is the mineral that you want to have if you're targeting those. So it's processed in Vietnam, this concentrate, and they do the acid baking in the concentrate, or in Vietnam, and basically produce a mixed rare earth chloride, which then they send to separate that into individual oxides. So this separation plant will be designed much differently than the one at Linus, because they're going to have much different rare earth distribution. They're going to be more weighted to the heavies. So they're going to have a different type of solvent extraction circuit set up to get that dysprosium out and so on, and different number of cells, because they have to go deeper into the rare earth distribution, deeper into the rare sequence to get dysprosium and terbium out. There's that separation between neodymium and samarium that allows you to break the lights out. And that's great for light rare earth deposits. But if you need to get that dysprosium, you got to go further down the line. So you need a different facility, sort of a different design. So often in the world, there's light rare separation facilities, there's heavy rare separation facilities, and then maybe there's like a magnet feed separation facility where you have, you might deplete the cerium and the lanthanum from a light rare carbonatite, and that has the right tolerance and distribution to fit that magnet feed facility, for example. There's flotation on the right, and at the bottom that's a bagged xenotime concentrate. That's about 20% REO. So they're that small producer I alluded to before. It's easy to mine, it's a laterite, so it's not that consolidated and so on, and they're able to produce a decent concentrate. They've been able to cost effectively so far process that through. This is some more photos. This is just the rotary kiln. So again, outdoors, this is going to be a low capex solution. In Canada or North America, you can't have that. That's going to have to be, indoors, if you will. There's a story in here about Quebec Lithium in Quebec where they built a mineral processing plant, but they didn't insulate it, and the mill froze in the winter. So it's like there's certain check boxes you have to do. That's solvent extraction. Those are mixer settlers up on the right. And at the bottom, that's part of the end of the kiln where they're doing the acid baking. So put sulfuric acid in there and so on and process that through. Break down the minerals. This is Dong Pao. These photos are thanks to Gerhard Merker. Very, very smart mineral processing engineer. Has worked with us on the Asheron deposit and had a lot of success. These deposits are in development. So there's Dong Pao and Namji in Vietnam. They're lateritic profiles. So again, you kind of have higher grade ore sitting on top in your laterite, and then you tend to have underneath your primary ore, which is lower grade, but more indurated, and it'll have more of your carbonates there. And so you have the fresh ore, you can see the Bastion site there. The very high grade ore, around 30% is that one there. And then your more weathered material as well. Namshi, there's an outcrop there, the weathered material. And when you go deeper down, you're getting into fresh material. And it actually has very unique, I wouldn't say unique, but it has parasite as its main mineralization. And so parasite is a calcium member of a rare fluorocarbonate group. So it's very closely related to bastnäsite. And they've been able to produce over 40% REO concentrate. So parasite is one of those minerals that has potential because it's very similar to bastnäsite, and it can hold, not as much, not quite as much rare earths in it, but it can hold a decent amount to get you over 40%. So if you see parasite, that's not a bad mineral. That's one of the good ones to look at. It has a good shot of being processed. And when we talk about monazite, bastnäsite, especially bastnäsite and carbonatites, it's by far dominantly mineralized in bastnäsite, but there might be a small component of monazite in there, a small component of parasite in there that gets mixed in together. But the recovery from that might be negligible, or it might be might process the same in those quantities, that sort of thing. But they're rarely purely monomineralic, is what I'm trying to say. I wanted to put a slide on Asheron. I'm project manager of Asheron, so I obviously have some bias. Just to put it out there, but it really is a truly a very good deposit that compares favorably if we just look at the metrics that we've chatted about. So deposits in the development phase, the ones before Dong Pao and so on, those are all producers. This is now in development. It's top ranked jurisdiction. This is positive. Large tonnage, moderate grade, so 1.9%. There are deposits in China that are operating, as low as 1%. Carbonatites, simple mineralogy, so monazite, bastnäsite, and also has xenotime in there. So this is an example of a carbonatite that's light rare earth enriched. So it's going to have a lot of NdPr. It's exactly what you want, but it has a heavy component with it. So it's going to have a higher value distribution because it has some terbium and dysprosium in it. The value is going to be driven by NdPr, but there's going to be a decent component of heavies that you can recover from it. So this gives it, on a per kilo basis, it's more valuable than Mountain Pass, for example, or a little bit more than Linus. If you have 1 kilo of rare earths, its distribution is going to have a higher value. That's not the same as value per ton, because that's where you're taking grade into account, right? But it's got very high value material if you can get it out. So you have to be able to process it efficiently, because you're going to have excellent material if you get it out. So it has, we're able to produce a mineral concentrate of greater than 45% REO at high recovery. And so this is critical. If that was 15%, that wouldn't cut it. It has to be large, because you need to reduce the size of your hydromet downstream, so on, your capex and so on. And so you have your highest value, you have very high value material, and you've concentrated it into a very small volume to push through your hydromet plant, smaller hydromet plant. It's also open pittable, strip ratio of 0.2 to 1. I don't think there's any rare earth deposits that are actually underground. I think Wushan started open pit, maybe pushing underground, but if you have to go underground, you're starting from a base of difficulty. Rare earth deposits are all mined essentially open pit. This one is direct from surface as well. So it has that going for it. So it clicks a lot of the categories. There's other ones that needs to click, but these are things that okay, yes, it needs a further evaluation, for example. And that purple up on the right-hand side, that's essentially where the higher value material is. So that grade, and that is actually about 1.7, 1.6. It is actually has higher dollar value per ton than the stuff that's actually higher grade at about 1.9. And it's because it has an even better distribution, weighted a little more to the heavies, and it has more neodymium compared to the stuff surrounding it. So even though it has lower overall grade, it has a higher value per ton. And at the end of the day, that's how you're going to mine it. Just a slide on potential secondary sources. So phosphogypsum, there's a lot of this produced in the fertilizer industry. It makes sense to look at it. It's low grade, about 0.5% REO. It's got large tonnages. It often can vary in content, and you don't really know where. It's almost like you have to explore to see really what the content is. So you have to design a facility that can handle that. It's difficult to get fertilizer companies to tack on something to their stream, for example, coming off to collect it. So, but there is a lot of this stuff produced. And so that's something that's of interest, and a lot of smart people are looking on that as a potential secondary source. Coal, there's a lot of chatter about coal over the last 5-6 years. The rare earths are concentrated in fly ash. So this is the glass phase. So remember when I talked about very fine grain being very difficult, this is fine grain in glass. It's difficult to get out. Very low grade, 500 ppm. It upgrades as you burn, as you combust. It might go to 300 to 500, something like that. But it is it's low grade. There's been significant capital invested by the U.S. government into looking at this. There's been some progress. I'm not personally, I'm not sure it'll work out because it's so low grade, and you have a lot of difficult, I guess, chemistry to figure out how to make that work. Often it's touted that there's the no need to mine aspect as an economic benefit, and of course that's true. If you don't have to mine it, those are costs that you don't have to pay, right? Every ton of dirt you move around at a mine site is one of the most expensive expenses of that mine. But the downstream hydromet is the most expensive part of most rare earth projects, pretty much all of them. So when I talk about making this high grade concentrate, there's a reason for that. It's removing all the potential problems downstream. I don't have to play whack-a-mole or any of that stuff, but it's reducing my capex and the size of my facility. And that's where a lot of the money is spent, and your projects are make or break. So these secondary sources, that is a positive, but it's not the be all and end all. You're always dealing with lower grade material, and there's always other hiccups you have to figure out. Uranium is a very interesting one. I really like uranium, actually. Processed streamer tailings. It's low grade, 0.5%. It depends. It's often heavy rare earth enriched, so this could be a good source of dysprosium and terbium. And there's precedent for it. It was recovered as yttrium in the 1980s at Elliott Lake in Ontario. So Canada used to be a rare earth producer on a small scale, 30 years ago, 40 years ago. So it happened. But there can Energy Fuels is looking at right now getting into uranium or getting into rare earth production. It uses similar chemistry, solvent extraction, if you will, is used in the rare earth space. That's also the main way to separate in the rare earth space. You can maybe bolt on a parallel circuit, but also if you could recover the tailings as they're coming off this effluent, then you can immediately bolt on a circuit and process it and get your rare earths out and maybe get that value out. Up in Athabasca Basin, they're very high grade deposits. So maybe, the highest grade deposit in the world, I think, is under 1 million tons or maybe 2 million tons. So you don't have a lot of rare earths potentially in there, but maybe in Kazakhstan or some of these lower grade deposits, they do have some. So it's something to look at. One concern I often hear about companies is that there's a lot of trepidation about disturbing tailings. So it's a very different thing to recover rare earths from sitting tailings there that are reclaimed or going to be reclaimed. There's a lot of liability there. But if you can tack on your circuit at the end of a thing, you can remove it and you're good to go. All right, last slide. Key considerations for success. Jurisdiction, challenging jurisdictions undermine potential for development. That's well enough stated, I think. Well-balanced distribution, again, you're going to be driven by the magnet feeds. You need to be weighted in the magnet feeds. The more neodymium, praseodymium, the better, and then have some of that terbium dysprosium. Remember, people are trying to engineer out terbium dysprosium, but they're trying to find new uses to the other lights you would produce if you're producing neodymium, praseodymium. The right rock, simple and gangue mineralogy, they both matter. Carbonatite rock types dominate production. That isn't going to change, current and historical. Monazite, bastite, and xenotime mineralogies dominate production, past and present. So, look at that as well. There's a reason for that. Simple conventional metallurgy, all these producers produce high-grade mineral concentrates apart from the clays. So you need to be able to do that. And you need to have a large tonnage at a favorable resource. Your typical granite countertop has a better distribution than most rare earth deposits, but it has no grade. So it doesn't make any difference, right? But you need to have a large enough tonnage, and you need to have a favorable grade in combination with all these things. And with that, I'd just like to acknowledge a lot of the Adamus Intelligence, Merkur Mineral Processing, Hazen, Kaz Machida, Clint Cox, and Alex Knox and Patrick Schmidt, all for their help and various contributions to the presentation and photos and so on. So thank you very much.
Wow, Darren, thank you very much. That was such a multifaceted talk. You went through, the market, processing, and even sources. That was really interesting. Thanks. So Irene is going to go over how people can ask questions, and then we'll start with the questions. The talk was a little bit longer, and so we might only have time for a couple of them, but we'll try to get to as many as we can. So the first question came on fairly early. It's by Michael Thompson, and it says, there are literally hundreds of rare earth deposits in the world. Other than those in China or Mount Weld or Mountain Pass, which deposits do you believe will be economic in the future?
That's a good question. Well, I'd start with the carbonatites. I think have the best chance. So obviously, I think Ashram is a really good one. I really like the Ngwala project in Tanzania. It's bastnasite. They can make a decent concentrate, a good recovery. The main negative there, though, is that it's in Tanzania, which isn't the best jurisdiction, and the mining laws have recently changed. There's a nice project in Angola, has good grade and decent tonnage. I can't remember the name of it offhand, but there aren't necessarily a lot. I think there's a lot that have challenges. There's some good ones in Australia, but some of them have incredibly high strip ratios. And one comment I'd throw out there is when you hear demonstration plant, it doesn't mean production. Those are usually heavily subsidized, and they're de-risking, and they're just doing it at a larger scale. So it's an important component, but it doesn't mean they reach commercial production. So when you hear that, sort of think about that. And I guess the other deposit I would say that I really like is apart from Ashram would be Wichita. It's got a good simple mineralogy. I'm not sure about its tonnage per se, and it doesn't have a very good distribution, but it's got some positive qualities that it needs to do a PEA and so on, and flush out some of those economics.
Mm-hmm. All right. Irene, did you have a question from YouTube at all?
Yes, no, from YouTube, we don't have any questions until now, but
Okay.
I do see another one that looks very interesting from our chat. So Chris Berry asked, what extraction technologies are you the most optimistic about going forward?
Chris, that's a great question too. Solvent extraction, it works. It's cost effective. You can get up to 5.9 purity. There's been a lot of work done, and a lot of companies pivoted to new technology is going to save everything and make us cost competitive with China. I don't think that's a solution myself. I think it's part of the solution where, but at the end of the day, you need to make it work on a solvent extraction because it's demonstrated and it works. I think there's some interesting technology called Rapid SX, which is a technology to do quicker solvent extraction. There are some negatives to solvent extraction. For example, it's not just turnkey. You can't just turn it on and it works. It takes time to the system to build up. So if you stop it, it takes a long time to get it back to equilibrium and to go again. But I think those are great. Electrophoresis, it needs to be proven out. It's a lot of energy. MRT, for example, is or ion exchange. These technologies are used for when you're at like 3 nines and you want to go to like 5 nines. Those can be really good. But in terms of separating everything, I think solvent extraction is really where you want to go. And for juniors in the industry doing that, if there's other companies like Rare Earth Salts or wherever also working on a technology, if they prove to be economic, you're gonna be able to license that technology, or you're gonna be able to potentially integrate it at that time perhaps. But because a lot of these companies are developing technologies apart from deposits as well, right? So it'll be part of their business model. But at the end of the day, solvent extraction, it works. And as new technologies developed, it can be integrated.
All right.
Thank you.
Yeah, thanks. So our next question is from, forgive me if I mispronounce this wrong, but I believe it's Georges Cassé. And they would like to ask a question regarding the distribution in carbonatites. So can a study of rare earth distribution in a carbonatite lateritic profile be enough to confirm whether or not a laterite is a potential deposit for rare earth elements?
You need more than just the distribution. You'll need to, well, you need to know the tonnage in the grade. The distribution kind of tells you where the value lies. You know, I made the comment about a granite. A granite has an excellent distribution, but its grade is so low at like 200 ppm, it doesn't matter because its grade's too low. So you can't look at any of these things on their own. You have to look at them in combination with each other. And this is where rare earths get very complicated for a lot of people. Sorry, I'm just gonna go to that one slide. So you have to look at the prices of the 4 main, but you have to include your tonnage and your grade is important. And so if you have a laterite, I want to know what the minerals are. I want to know their grain size. If it's 2 microns, I'm not interested at all, because that's going to be incredibly difficult to process. You know, if you're 10 microns and above, you're doing a lot better. You know, what are the associations of, is there a lot of interlocking grains? How complex are they? That sort of thing. And how you know, deeply weathered is it? If it's just a small profile, then it's not your main ore body, for example, then maybe it doesn't make any sense. So I guess what I'm trying to say is it doesn't start or stop with the distribution, but it's a very important component to know where your value is going to be in the market. And in my opinion, the best distribution to have is one that is a light rare earth. It's always been light rare earth in my opinion, because neodymium is the driver. It is the one that if they substitute more of it. If they have dysprosium, they try to get it out. Terbium, they try to get it out. So if I want long-term viability, I want to have the maximum amount of neodymium I have. So you want to be 20 or above, or 25 or above or higher. And then ideally you have some heavies that come with that, but the main value is going to be in that NdPr. That's where you want to be weighted.
Thank you, Darren. We have so many great questions. You guys are making our job really difficult. Well, I have a golden question here from Vladimir Ispolatov. He's asking, are there any districts or provinces with untapped potential?
The world was combed over pretty good over the last 10 years. So I used to know all the deposits. There's some more that have been developed or have moved forward over the last couple of years, but I say the chances of discovering something new, those times have really passed. You know, same with lithium in the lithium space. During the lithium boom, a lot of exploration happened. Every company was going to lithium, because if you can raise money on it, you're exploring it, and so on. And so in the rare space, I think any new discoveries would be surprising. And I think if there's stuff that is existing, that is where those are going to have the best chance of success. And you know, one thing that's sort of changed over the years is most separation facilities would have 2,000 to 5,000 tons a year, and that would be the production profile of a rare earth project. Their economics would be based on that. Well, Linus and Mountain Pass have sort of proven that you can do economies of scale at rare earths, that you can do 20,000 plus. So you're now tonnage is becoming is very important, because if you can handle economies at scale, this can help make you a lot more successful. So large tonnage with the proper distribution, you know, good mineralogy, right grade, I don't think there's going to be new discoveries outside of what we've already found.
All right, thanks. We have, so you mentioned granitoids, so we have a quick question from somebody who wanted to ask about the granitoid. So Alexi, would you like to unmute yourself and ask your question yourself? All right, we'll just go ahead and ask it for them. So the question is, what factors would you look for inside a granitoid deposit?
Grade. Usually they tend to be lower grade than 1%. So if you can get something higher, that's great. Number of rare earth minerals and what they are going to be essentially the main things. They tend to be a lot of complex mineralogy, and not just complex rare earth minerals, but also complex gangue. And so the first thing I'd want to know is, can I apply X-ray sorting to separate that gangue? And what are the rare earth minerals, and how are they all complexed with other minerals in the deposit? That's the first thing I'd want to know. But for granitic deposits to work, there needs to be a really good distribution, and they need to be open pittable, and they need to be in a really good location. And you need to be able to make good mineral concentrates. A lot of times granitoids come with zirconium, niobium, maybe even fluorspar. And a lot of times companies try to complicate their flow sheet by bolting on niobium to get that out to make the project work more money, and get scandium out or get this out. And at the end of the day, it needs to work essentially on its rare earth content alone. So I'd focus directly on the rare earth content and immediately on the mineralogy. Because if that mineralogy isn't looking like it could be sorted out, then you're going to be for a long slog in the R&D department.
All right, I'd actually like to sneak in a question of my own right here, because you're talking about in terms of a deposit, you really need to focus on the rare earth content alone. So when you mentioned that rare earths are also a byproduct of iron ore processing, is that also a situation in which you should probably only focus on either the rare earths or the iron ore, as opposed to combining them together?
In that case, it really only happens at Bionoble, where it was iron ore mine, and then they just sort of discovered rare earths and how they could get it out. It's a very unique deposit. It's got carbonatite affinities and so on, but you're going to find, I mean, there's some IOCG deposits that have rare earths in them. There's some other breccia deposits that have some rare earths in them. They tend to be small or lower grade. But at the end of the day, at Bionoble's case, it's the fact that it has the right minerals. It has monazite and bastnasite. So they're able to efficiently get that out, and they're able to get that to a high grade mineral concentrate. So if I had like eudialyte, for example, the problem with eudialyte is that it just doesn't hold a lot of rare earths. And it's focused solely on dysprosium. So I have the elements that everyone's trying to engineer out, and I have, at best, I can get an 8% rare earth concentrate. That's a lot of stuff going into solution. And for me to get the equivalent amount of output that a carbonatite would, I have to process a whole lot more of material. So I guess that's a roundabout answer, but in Bionoble, it's very different. So if I could bring it around to ashram, for example, ashram is a unique case as well, because we produce a rare earth concentrate, and we knew we had fluorspar there, and it upgrades passively through our flow sheet as a tailings product. So we knew we didn't announce that we were interested in that being a byproduct until we were sure it wasn't going to complicate the flow sheet or negatively impact the rare earth recovery. We don't have to bolt on another circuit to try to pull out the value of fluorspar. It's the tailings of our rare earth concentrate. So instead of going into the tailings impoundment, we can sell that for value and pump back into the company. So that sort of byproduct is very positive. The sort of byproduct where you have to bolt on additional circuits, this is where you're adding technical risk, capex risk, and so on. And there's a deposit in Canada that initially did that, trying to get niobium out, zirconium out, and they did a PEA, PFS. They went all the way back to the drawing board, focused just on rare earths, managed to get a pretty decent concentrate for a granitoid, and the project is much better positioned now, I think, because it's not complicating the capex and everything with those other circuits. So it depends how the byproduct is done. And in mineral sands, for example, it's a true byproduct because it's driven by rutile and ilmenite. So no rare earth deposit, no two rare earth deposits are the same. And that's a really difficult point to get across sometimes, is that they're all very different and they all require different flow sheets. So you can't just take feed from two and put them into one. There have to be very similar in order to do that, and that can be difficult.
Mm-hmm. All right.
Thank you so much, Darren. I have a question that sort of follows this. It's done by Juan Carlos Sarmiento. I don't know if he wants to ask it himself, so I'll give him a couple of seconds. He's connected. No, well, if not, is it possible to benefit from rare earths from sulfide tailings from deposits of polymetallic skarns like lead, zinc, or copper that contain moderate values of rare earth elements? I would like to add to that also IOCG deposits, as you just mentioned, and what metallurgical flows would be optimal and what are the OPEX?
I can't really comment on the OPEX part, apart from saying that it depends what the concentration of the rare earths are. You don't usually get concentrations of rare earths in skarn deposits or things like this. And so you might not have that high concentration. And so, you know, it's like, you know, rare earths could be in very low concentrations in a lot of different rock types, but it doesn't mean that they can necessarily be extracted. So, you know, acid rock drainage is something, for example, that could be looked at on certain projects. So I think uranium, I think, is honestly one of the best effluents to really look at. And polymetallic deposits, maybe there's some there, but I don't think it's going to be in very high concentrations at all. And I'm not sure it's going to make a lot of sense to try to get it out. But again, those are some trade-off studies that have to be done.
Sorry, may I ask a question? I'm there now. I don't.
Yes.
In the last weeks, I read a couple of announcements from the United States and from Canada, above all, to develop big rare earth projects. For example, Saskatchewan to develop become a big rare earth production center. How serious is that all?
I think they're pretty serious. I mean, the SRC, Saskatchewan Research Council, are very smart people and very capable. And the Saskatchewan government has put money down and basically to help build this plant. And their idea is to take in feed from basically light rare earth deposits in the area. So ones that have basically monazite and bastite dominated lithologies. And they want to see if you can process them all together, combine all their ore into one, process it in the same flow sheet. That's the holy grail in the rare earth space, because they all have different impurities, different things. They're all very different. And so if they can do that, that's fantastic. And I'm happy to see money put down for that work to see if it can be done. But I also think that a lot of what they're doing is going to be more of a demonstration plant for getting rare earths out of the uranium effluent, because Saskatchewan is one of I think the world's second largest uranium producer behind Kazakhstan. And so there's a real potential to collect some rare earths from that. I think it comes off in the raffinate of the solvent extraction, as they could strip it off or something, but it tends to occur in uraninite and so on. And so you can get some decent rare earth deposits, although just low tonnage in the Athabasca Basin. So I think it's a step in the right direction. It doesn't establish a secure value chain per se, because again, they're just doing the one part of the chain. But what it means is that it's another component in place. You know, the mining is in North America. The next step is getting there as well. And, you know, maybe from this, it helps facilitate more investment into like metal making or something like that. I think Quebec, for example, has a good opportunity to enter the metal making space. They already do similar processes with your aluminum. They have some of the lowest cost energy here. They're very forward thinking on the environment. There's a lot of smart people here. I think that's something that could pull the market in this direction. And so it's a good step in the right direction for Saskatchewan and the SRC.
Thanks.
All right. And I think because of time, we're going to have one last question, and it kind of tacks on to the one Gerhard asked about Saskatchewan. So this question is from Liam Ma. Liam, are you there, and can you unmute yourself to ask your own question?
Yeah, that pretty much addressed it, really. I was mentioning that the Saskatchewan said they're going to build that by 2022 with a relatively low price tag for what you would assume for a mineral processing plant. And do you think that a plant first approach is better than matching metallurgy to a given deposit, considerably with the challenges of metallurgy for these minerals? And you think that could help solve supply chain issues and encourage development of byproducts from uranium raffinate?
I think the $31 million price tag was the most surprising thing to me, because if you look at every single junior, essentially North America, that designs a hydromet facility for their project, we're talking hundreds of millions of dollars. They could do it for 10, 20, 30 million in China or so on, but over here it's significantly more. So I think it's probably more demonstration level to maybe focus more on uranium, but there's a lot of value there, and looking at the idea of combining these concentrates. Do I think it will work? I think that if you have, it works in China in the sense that you have, Bao'an Noble produces a monazite bastnasite concentrate. Maoping produces a bastnasite concentrate. If you have the same feeds always coming in from the same mines that always operate, then you blend it. You're going to have a constant feed at that point. The problem in Canada is that you maybe don't have any mines go into production. Maybe you have 5 go into production and then 2 leave. Your distribution of your concentrate completely changes. And so what has to be designed is a facility that can handle all these very tolerances in the concentrates. And I think that's very difficult and maybe isn't going to work. I think what might make more sense is to every company that goes into production, they carry their project through to their mineral concentrate, they break it down themselves, they produce a mixed rare earth carbonate, so intermediate product. At that point, all the deleterious elements are gone. Everything is the same, except distribution is a bit different from one deposit's intermediate product from the other's intermediate product. But if you have all light deposits or all rare earth deposits, like say what Cheetah gets into production, or Cheetah or Appia or Commerce, for example, all these are essentially monazite or bastnasite dominated deposits. So you could potentially design a light rare separation facility that could accept any blend of those 4 or 5 mixed rare earth carbonates. So you get the whole range of tolerances, and then they could process it through. I think that probably makes a lot of sense from my perspective, because it is a holy grail to be able to take, whatever deposits, throw them together and process them. But really the base saleable product is if you have monazite and bastnasite mineral concentrate, you can sell that or process that. If not, then really it comes down to the mixed rare earth carbonate stage. And so I think that is probably the most logical. But at the end of the day, all that can also be irrelevant in the terms that it has people talking about the supply chain, has people talking about rare earths. There's been a government that's put investment in, and there's been some smart people that investment has gone to, and they're going to start pushing stuff forward in some aspect of the value chain. I think the only way a value chain gets established here is if it needs to be government subsidized. It needs to be a lot of money put in and make it happen. This is what happened in China. You can't just build a separation facility and have it all there, but that is one piece. And I think it's a step in the right direction. Will it be successful? Maybe ultimately not, but I think they'll definitely do a good demonstration plant. They'll advance the work on the uranium raffinate, and they'll make some positive developments in terms of processing, and there'll be a lot of R&D that's developed. NRCan is a great RE program that the federal government started 6 years ago, and there's been a lot of funds put into research and new technologies, but also on it's really educated the academic world and the scientific world and the research world on rare earths. And I think this is a big positive from this investment. It should lead to more, I hope.
Perfect. Thanks.
Well, thank you so much, Liam, for your question. And yeah, Darren, you've had so many positive comments about the quality of your talk and how thorough it was. So thank you very much. And yeah, this is the end. We're gonna sign off here. And thank you, Darren. Thank you, everyone who participated. And we're very sorry if we weren't able to get to your question. And yeah, join us next week.
Thank you very much for the opportunity.
Mm-hmm.